We are now going to study the pneumatic system. The pneumatic system consists of two subsystems: the pneumatic power generation and distribution. We are now going to study the pneumatic system. The pneumatic system consists of two subsystems: the pneumatic power generation and distribution, and the wing ventilation system. The pneumatic system is supplied by three sources: the engines, the APU, and a HP ground cart. The air supplied from these sources is used to operate the air conditioning system, the wing anti-icing system, the drinking water pressurization, the engine starters, and the thrust reversers. Let us have a look at the pneumatic panel located at the flight engineer station. You can easily follow the flow of the bleed air by looking at the synoptic diagram from bottom to top. Let us first see the engine air supply, which is identical on both sides. The purpose of the pneumatic system is to limit pressure and temperature. Let's see first pressure regulation. The bleed air is taken from the 8th stage or 14th stage, depending on demand. Normally, in-flight air is taken from the 8th compressor stage. A check valve prevents the 14th stage high pressure from returning to the engine. The 8th stage is called the intermediate pressure stage, or IP stage. Under certain conditions, such as low engine speed, the pressure from the IP stage is insufficient. In this case, the air is taken from the 14th stage. The 14th stage is called the high pressure stage, or HP stage. The air then passes through an HP bleed valve. It is electrically controlled, pneumatically operated, and spring-loaded closed. The air from the 14th stage is also used for the hydraulic reservoir pressurization system. The HP bleed valve is controlled by a three-position selector. The position of the valve is displayed by a magnetic indicator. The HP bleed valve is commanded to close when the selector is at close, or automatically when the selector is at auto and pressure from the 14th stage is more than 86 or 141 psi. The different valves depend on the status of wing de-ice. From where does the pneumatic supply come? The bleed valve reduces the pressure to 46 psi and is used as a shutoff valve. It is electrically controlled, pneumatically operated, spring-loaded closed, and fail-safe open. The bleed valve is controlled by a three-position selector. The overpressure valve is a strictly mechanical valve and isolates the system in case of overpressure. System pressure is displayed on a pressure gauge via a controller. The bleed air is now pressure regulated. Let's see temperature regulation, which is done with a pre-cooler or so-called heat exchanger. The amount of cool fan air is regulated by a fan air valve. It is electrically controlled, pneumatically operated, and spring-loaded closed. After the fan air passes the pre-cooler, it is discharged overboard to the atmosphere. The bleed air temperature is monitored by two temperature sensors. One sensor sends signals to the temperature indicator. The second sensor sends signals to a pneumatic controller. The pneumatic controller controls with the input signals the fan air valve for a temperature of 177 degrees or 227 degrees Celsius. Here are the temperature and pressure indicators on the pneumatic panel. Warning lights will display any fault from the pneumatic system. Automatic closure or opening of the HP bleed valve is a function of which parameters? Now let's see the second supply, the air from the APU. Here it is not necessary to regulate the pressure or temperature because the air leaving the APU is within the values we need for the system. Therefore, the APU bleed valve is a simple shutoff valve, electrically controlled, pneumatically operated, and spring-loaded closed. A three-position selector is for the APU bleed valve. Valve position is indicated by the magnetic indicator. To open this valve, the APU must be running in a certain condition. A check valve prevents pneumatic air from returning to the APU bleed valve. There is also a connection to the hydraulic pressurization system. The APU duct supplies the left pneumatic manifold. To supply the right side, the cross bleed valve must be in the open position. Let's now see the last source, the high-pressure ground cart connection. There are two 3-inch standard connections for a HP ground cart supply. The air also enters the left pneumatic manifold, and to supply the right side, the cross bleed valve must be opened. You can easily follow the flow on the synoptic diagram to the left pneumatic manifold and the cross bleed valve. The cross bleed valve is electrically controlled. Normally, when both engines supply their manifolds, it is closed. The rotary selector has 4 positions. An amber fault light illuminates when the valve is in transit or in disagreement with a selected position. After engine start, the supply to the pneumatic system will be changed from the APU to the engines. This is to avoid engine exhaust smell in the cabin during taxi. For takeoff, we again use the APU supply to keep maximum performance of the engines. For a quick change from the APU supply to engine supply, there is an automatic sequence with the APU bleed valve switch. When the APU bleed switch is in the closed position, the bleed valves are free to open and the cross bleed valve is closed. When APU bleed switch is selected to auto or open, automatically the cross bleed valve will open. The bleed valves will receive a signal to close even if they are selected to open. What switch configuration will allow the high-pressure external air to operate the left and right pneumatic systems? Now let's see the second subsystem from the pneumatic system, the wing ventilation. The purpose of the wing ventilation is to maintain an acceptable temperature in the wing leading edge between the pylon and fuselage. In this zone, hot air ducts would otherwise cause the temperature to rise too high. The ram air intake is for flight operation. During ground operation, airflow is induced by a fan. The ground inlet is opened or closed with a flap driven by an actuator. The operation of the fan and actuator is controlled through the landing gear air-ground logic. Situations are indicated by magnetic indicators. This concludes the presentation of the A300 pneumatic system. This presentation will cover the electrical power system of the A300. Two engine-driven AC generators supply the primary power, each generator feeding its respective AC load bus with 115-volt, 400 hertz, three-phase AC power through a line contactor. Generator 1 to AC load, bus number 1 and generator 2 to AC load bus number 2. Either or both of these two power sources can be replaced by the APU generator within the APU flight operating envelope. The philosophy of the electrical system is such that one AC load bus can never be supplied by two sources in parallel. An automatic control circuit prevents parallel operation. An external power source rated at 115-volt, 400 hertz, three-phase AC power can also be used to supply the entire aircraft. DC power is normally obtained from three transformer rectifier units connected to AC load buses 1 and 2 and the AC essential bus. In case of emergency conditions, 3 batteries can supply the DC essential circuits. A static inverter producing 115 volts, 400 hertz, single-phase AC power is used as an emergency source of electric power. It is available as soon as a source of DC power is on the aircraft, such as when a battery is turned on. Let's try a question now. AC generators are used in what configuration? A, parallel, B, non-parallel, C, both A and B, depending on the situation. B is the correct answer. Remember, an automatic control circuit prevents parallel operation. Great care has been taken to prevent this possibility, even under failure conditions. Now take a look at the electrical power control panel located at the second officer's station. The flow of the electrical power is schematically engraved in the panel from bottom to top. Before looking closely at the electrical control panel, it is important to know that the illumination of any amber light will be accompanied by the illumination of an amber electric light on the master warning panel and the single-stroke chime. The first part of the electrical panel we are going to present is the CSD oil temp panel. Each engine drives its associated generator through a constant speed drive, or CSD. The constant speed drive ensures a constant frequency output of the generator. In the event of a malfunction, the CSD can be disconnected from its drive shaft. Two indicators show the temperature of the CSD oil taken at the outlet of each CSD. Normal indication is below the yellow arc with the red line showing the maximum limit. When pressing the push button marked CSD temp push for rise, the differential between oil in temperature and oil out temperature of the constant speed drives is displayed simultaneously on both oil temperature indicators. Normal indication is below the yellow arc of the inner scale. An amber oil pressure low light located on the bottom of the electrical control panel will illuminate when the CSD oil pressure detects a drop in pressure below a predetermined value. This oil pressure low warning light is inhibited when the corresponding engine high pressure fuel shutoff lever is in the off position. A CSD disconnect guarded switch will permit us to disconnect the CSD in the event of a CSD or generator malfunction. Once disconnected, the CSD can only be reconnected on the ground by maintenance personnel. A note of caution: the disconnect position of the switch must not be maintained for more than 3 seconds. For review, there are associated with each CSD an oil temperature indicator which displays directly the oil out temperature or the differential temperature between oil in and oil out when the CSD temp push for rise button is pressed, an oil pressure low amber warning light, and a switch to disconnect the CSD from the associated engine. One generator off light is provided to monitor the operation of each generator. This warning light will illuminate amber when the associated generator control unit detects a fault in the generator circuit, or when the associated generator selector switch just above the light is set to off reset. A 3-position generator selector switch, when held to the test position, will enable the generator parameters to be checked without a load on the generator. If a fault is detected, the generator off light will illuminate. With the generator selector switch set to the on position, the generator will be connected to its associated AC load bus. This action can be verified by an indicator which is calibrated in percentage of rated output. The figure 1 means 100% of the rated output, equivalent to 90 kVA. The indicator shows 0 when the line contactor is open. A line control switch located above the load indicators permits manual opening of the line contactor when set to off. When set to normal, the line contactor will close automatically when normal generator parameters are sensed by the generator control unit through an interlock system. Each line contactor is controlled by the interlock system when the line control switch is set to normal. The line contactor will open if the voltage, frequency, and phase sequence are not within the prescribed limits, or when the generator selector switch located above the generator off light is set to off reset, or when the CSD disconnect is set momentarily to the disconnect position, and finally, if the CSD speed is less than 95%. If any of these conditions occur, the generator off light will be illuminated. So to recap, each generator supplies an AC load bus through a line contactor monitored automatically by an interlock system called transfer logic and manually by a line switch. Generator output is displayed on an indicator in percent of rated output. A generator off light illuminates when the generator is no longer connected to its associated AC load bus. Let's see if you can answer this question. What value is provided by this indicator? A, kVA, B, amps, C, percent of rated output. C is the correct answer. If a generator load is too high, the amber generator load high light will illuminate. Load shed switches, which control the power to the main and secondary galleys and to cabin service items, may be used to reduce the load. Another possibility of supplying the aircraft with AC power is the APU generator. The APU generator is identical to the engine-driven generators with one exception. It does not require a constant speed drive. An APU generator selector controls the operation of the generator within the same parameters as the other generators. If the prescribed parameters are not correct, the generator control unit will prevent the APU generator from feeding the AC load buses. An indication of this would be an illuminated amber APU generator off light. A significant difference between the generator off light on the APU generator as compared to the other generator off lights is the fact that the APU generator off light is operative only when the APU generator speed is above 95%. For example, the APU speed must be above 95% and the generator control unit sensing a fault before the generator off light will illuminate. A generator load indicator, identical to the other load indicators, has been provided for the APU generator. The APU generator can be connected to both AC load buses, but cannot be paralleled with the other generators. It is capable of supplying the entire aircraft except the main galley loads. The main galley load switch needs the output of two generators before it can be turned on. The interlock system ensures the transfer. In normal operating conditions, the AC load buses will be supplied by their own generators with the transfer relays open. Transfer logic ensures AC load bus operation without paralleling generators. Two transfer switches allow manual control of the transfer relays. Magnetic indicators monitor the respective transfer relay condition. When set to norm, the transfer switches allow control of the relays from the transfer logic circuits. When set to off, the transfer relays are opened. So, it is possible to supply one or both AC load buses with the APU generator or two buses with the same generator. For a review, the two AC load buses are always supplied by only one generator, never by two in parallel. Manual control of the line and transfer relays is possible, but in normal operating conditions, it is achieved automatically by an interlock or transfer logic system. Now, to test your memory, here is a question. Select the correct statement. A, generator 1 is connected to AC bus 1. Generator 2 is connected to AC bus 2. B, APU generator is connected to AC bus 1. C, generator 1 requires a reset to increase AC load. Of course, A is correct. As we said earlier, generator 1 normally supplies AC load bus 1. Generator 1 also supplies the AC essential bus through AC load bus 1. The AC essential bus in turn supplies the AC emergency bus. This condition is controlled by an AC essential bus rotary selector. This rotary selector also permits several different selections of power to the AC essential bus to be made if the need arises. By turning the rotary selector to the APU generator, generator 1 or generator 2 positions, power is taken directly from the output of these positions and applied to the AC essential and AC emergency buses. The emergency inverter position starts the emergency inverter and applies its output directly to the AC emergency bus. This action also divorces the AC emergency bus from the AC essential bus. An amber warning light will illuminate in case of a power failure to AC bus 1, AC bus 2, and the AC essential bus. These lights are labeled AC bus 1 off, AC bus 2 off, and AC essential bus off. When one of these lights illuminates, the amber electric warning light on the master warning panel will illuminate and the single-stroke chime will sound. Since the AC emergency bus receives its single-phase power normally from the AC essential bus, one would think that a failure of the AC essential bus would render the AC emergency bus inoperative. Regardless of the position of the AC essential rotary selector, whenever the AC essential bus is de-energized, the emergency inverter will automatically start up, delivering its single-phase power to the AC emergency bus. This action requires that at least one battery switch be on. A magnetic indicator between the AC emergency bus and the emergency inverter will reposition itself in line to show the emergency inverter operation. Two indicators are installed on the electrical control panel to display AC voltage and frequency for all phases of the supply selected by the two rotary selectors directly under the two indicators. Let us sample your knowledge of the electrical system with these last two questions. What buses does AC generator 1 normally supply? A, AC bus 1 and the AC essential bus. B, AC bus 1, AC essential bus and the AC emergency bus. C, AC bus 1 and the AC emergency bus. As we said earlier, generator 1 supplies AC load bus 1, which in turn supplies the AC essential bus, then to the AC emergency bus. B is the correct choice of answers. Complete this statement. The emergency inverter is A, automatically controlled and DC power supplied. B, manually controlled and DC power supplied. C, automatically controlled and AC power supplied. A is perfectly correct. When there is no power on the AC essential bus, the DC-powered emergency inverter will automatically supply the AC emergency bus with single-phase 115 volts AC. Answer B could be correct, but manually selecting the emergency inverter is not considered as normal operations. Let us discuss the DC generation system now. DC power is delivered by 3 transformer rectifier units rated at 28 volts DC and 150 amps maximum output. AC load bus 1 supplies TR1, AC load bus 2 supplies TR2, and the AC essential load bus supplies the essential TR. Corresponding TR switches control reverse current contactors on the output side of the respective TR units. After these switches are set to on, the outputs of TR1 and TR2 will be connected to the DC normal bus, and the output of the essential TR will be connected to the DC essential bus. A respective TR off light will illuminate when the associated TR is off. This condition will occur when the respective TR switch is in the off reset position. In TR overheat conditions, in reverse current conditions, or when the output of the TR is less than 3 amps. A DC tie switch controls a reverse current contactor which connects the DC essential bus to the DC normal bus. When set to the norm position, the reverse current contactor will open or close automatically to prevent the DC essential bus feeding the DC normal bus. A magnetic indicator will show the position of the reverse current contactor in line when closed, cross line when open. When the DC tie switch is set to split, the reverse current contactor is open and the magnetic indicator is cross-line. This action permanently splits the DC normal bus and the DC essential bus. 3 aircraft batteries are also connected through contactors to the DC essential bus. The 3 batteries are rated at 25 ampere hours with a non-voltage of 25 volts. So we can say that the DC essential bus has 3 sources of power in this order. First, the essential TR, second, the DC normal bus, and third, the 3 batteries. The contactors of the 3 batteries are controlled by battery selector switches. When set to normal, the battery contactors are controlled by charge limiter units. These charge limiter units will keep the contactors closed until the battery is fully charged, and then will open the contactors until the DC essential bus voltage drops below a predetermined value. The position of the contactors is shown by a magnetic indicator. These charge limiter units will also protect the batteries from an overheat condition. When an overheat condition is sensed, the charge limiter unit will automatically open the contactor, the magnetic indicator will turn amber, accompanied by a battery temp highlight on the master warning panel and a single-stroke chime. When the battery selector switches are set to the on position, the respective battery contactor is closed and the charge limit unit is inhibited. All protection is lost. When making an approach using the auto flight control system land mode, signals are delivered to the essential system to split the DC normal and DC essential buses and to connect the 3 batteries to the DC essential bus. This will be done automatically, provided the switches are in the normal position. The 3 batteries are equipped with an air cooling system. When smoke is detected in this cooling system, a red battery smoke light will be illuminated along with a red smoke light on the master warning panel and the repetitive chime. When the refuel on battery blue light is illuminated, it indicates that the refueling circuits are operative and connected directly to the output of battery 1, regardless of battery 1 switch position. Even if all the battery switches are turned off, the following equipment will still be supplied: the refueling system and the clocks by battery 1, and the engine fire squibs, the cargo fire squibs, and the ground mechanic call system by battery 2. 2 indicators are provided to display DC voltage and amperage indications as determined by the DC volt amps rotary selector. In the essential bus position only, bus voltage will be indicated. Let's try a question now. With the APU generator on and transfer 1 switch in the off position, which amber warning lights will be illuminated? B is the correct answer. With transfer 1 contactor open, AC bus 1, TR1, essential TR, and the AC essential bus are no longer supplied. Before we proceed to the external power supply system, look at the general view of the electrical control panel and review what has been discussed this far. Now here's a third possibility of supplying the aircraft with AC power. This can be done by an external power supply providing 115 to 200 volts, 400 hertz, 3-phase AC power. The external power supply is controlled by an external power control unit located in the main bay. When any of the listed conditions exists, the external power will not be supplied to the aircraft. A blue external power available light on the electrical panel will illuminate when external power is connected to the aircraft and all the parameters are correct. This light indicates that external power is available and ready for use. When the magnetically held external power switch is set to the external power, the AC load buses may be supplied through a ground power line contactor and the transfer contactors. When connected, a white external power on light will illuminate. From this point on, as soon as a fault is detected, it will automatically remove the external power from the aircraft. When both the APU generator and the external power unit are available, the first one established will have priority. However, when an engine-driven generator is available, it will have priority for its respective AC load bus, and the transfer logic system will do the necessary switching automatically. In order for the aircraft to be serviced by maintenance personnel on the ground, a system has been provided to power certain buses without powering the entire aircraft. With the external power available and the external power switch off, an AC ground flight load bus can be powered directly from external power output. An AC ground load bus will be automatically connected to the AC ground flight load bus. A fourth TR unit, the auxiliary TR unit, can only be supplied by external power and will power the DC ground flight load bus. A DC ground bus will be automatically connected to the DC ground flight load bus. The control of these buses on the ground is through a maintenance switch located on the forward circuit breaker panel in the cabin overhead by the flight deck door. Now take a look at the panel presentation of the external power controls and indicators. Review in your mind the function of each. Let's try 2 questions before we carry on. Which power source is supplying AC bus 1 and AC bus 2 under these conditions? A, the external power unit. B, the APU generator. C, generator 1. B is an excellent choice. The APU generator is operative as shown by the load indicator, and both transfer contactor magnetic indicators are in line. External power is available, but not turned on. Which power source supplies AC bus 2? A, the external power unit. B, the APU generator. C, generator 1. C is correct because the load indicator of generator 1 is the only one showing a load indication, and the transfer contactor magnetic indicators are in line. 2 red warning lights, main bay smoke and flight deck smoke, signal the presence of smoke in their respective areas. If either one of these lights illuminate, it will be accompanied by the red smoke light on the master warning panel and the repetitive chime. Special striped areas on the electrical panel help crew members to locate and identify specific warnings and switches used during fire or smoke procedures. A fireproof compartment located below the right-hand electronic racks and called the minimum equipment bay contains certain important equipment such as VHF COM1, public address system, fuel reserve low-level detection unit, engine 1 and 2 fire detection units, smoke detection unit, engine 1 bleed air control, and the crew oxygen control unit. It is monitored by a red minimum bay smoke warning light on the overhead circuit breaker panel and associated with the red smoke light on the master warning panel and the repetitive chime. A duct whose outlet is located below the right side of the second officer's table allows the minimum equipment bay to be checked for smoke by smelling the air coming out of the duct. A fan draws air through the duct from the minimum equipment bay and is controlled by a switch on the second officer's panel. Located on the electrical panel is a minimum equipment switch. When this switch is set to the minimum equipment position, only that equipment supplied by the essential AC, DC, and AC emergency buses located in the minimum equipment bay will be operative. Also, a small portion of the main bay and flight deck equipment will be operative. In other words, you will have sufficient power to aviate, navigate, and communicate safely. Close to the minimum equipment switch is another switch labeled Smoke Drill Nav Select. When set to the land position, it will restore a portion of the AC emergency bus that was eliminated previously by the minimum equipment switch. This will assure sufficient equipment to make a safe landing. Two galley power control switches on the lower left side of the electrical control panel control the power to the main and secondary galleys. The main galley needs up to 49 kilowatts and is powered by both AC Load Bus 1 and AC Load Bus 2. The secondary galley needs up to 15 kilowatts and is only powered from AC Bus 1. The main galley control switch is magnetically held to the norm position. Both AC generators are required for this switch to hold in norm. The switch will trip to shed if one generator is lost. The secondary galley switch is also magnetically held to the norm position, providing generator 1 is powering the aircraft. DC holding power for both switches comes from the DC normal bus. To prevent overloading of one generator, when a power transfer takes place, both galley control switches will trip to the shed position. If one of the AC bus off lights is pressed to test, this action will also trip the galley control switches. Note that when external power is supplying the aircraft, both galley control switches can be set to norm. The cabin service control switch allows power to be applied to passenger reading lights, cabin sidewall lights, passenger service units, and the logo lights. This switch is of the lock toggle type and will not trip off as will the other two. Now for the last question before we finish the electrical system. The system was running normally with generator 1 and 2 operative. Then due to a fault, generator 2 is lost. Which galley load switches will be automatically tripped? A, the main galley switch. B, the main and secondary galley switches. C, the main, secondary, and cabin service switches. Remember, the main and secondary switches will automatically trip when a power transfer takes place. In this case, the secondary switch can be restored. The cabin service switch is locked to norm, so B is the correct answer. This is the end of the electrical system presentation.
Eastern Airlines now presents the A300 air conditioning system. The purpose of the air conditioning system is to maintain an acceptable temperature, pressure, to renew the air, and to cool the equipment. During this presentation, we shall see the supply portion, the cooling part, temperature regulation, distribution, and pressurization. The management is carried out from the second officer's panel. The supply comes from the pneumatic system. This can be from the engines, APU, or external cart connection. The supply system is controlled by a pack valve. The pack valve is operated by an electrical motor, and its transit time is about 45 seconds. The reason for the slow transiting is to avoid sudden pressure surges in the cabin. The second valve is the flow regulating valve. It is electrically controlled and pneumatically operated. This valve controls a maximum flow so that the air renewal rate is within limits at all altitudes. Both valves are controlled by the same switch. A flow indicating gauge reflects the amount of airflow through the valves. The fault light is a disagreement light for the two valves. What do these gauges indicate? The air is then divided and part of it enters the pack or air cycling machine for the cooling process. The rest of the air bypasses the respective pack. The hot air which enters the air cycle machine is cooled down to the level of the lowest compartment temperature demand. The cold air which leaves the air cycling machine then flows to the cold manifold. The air cycle machine is controlled by the pack control switch either in the auto position by means of a controller or manually. The pack parameters are displayed on these instruments. In case of a dual pack failure, the ram air inlet supplies the cold manifold in order to cool the avionic racks. The control switch controls an actuator which drives a flap. Flap position is indicated by a magnetic indicator. Part of the hot air from the pneumatic supply does not enter the packs. This second flow bypasses the packs to supply hot air to the hot manifold. The supply valves to the hot manifold are trim air pressure valves, which are electrically controlled and pneumatically operated. Both trim air pressure valves are controlled by one switch. They regulate the hot manifold pressure 4 psi above cabin pressure. If one of them should fail to regulate the pressure properly, a pressure switch triggers the trim air pressure high light. Trim air is available from Let us now turn to the temperature regulation. This is done with air from the cold manifold, color-coded red. In order to achieve proper control of temperature regulation, the cabin is divided into 4 zones: the flight deck, the forward, middle, and aft compartments. Each zone is supplied with air from the cold manifold, and the temperature is adjusted by means of trim air from the hot manifold with electrically driven temperature control valves. A temperature control valve is controlled by a rotary selector, either in the automatic mode via a controller or in the manual mode. Above the rotary selector is an indicator which displays the position of the temperature control valve. The temperature highlight illuminates amber when there is an overheat of more than 88 degrees centigrade in the duct leading to a compartment. A dual temperature indicator will indicate the duct and compartment temperature. These temperature highlights indicate Next, we will see the distribution, which includes delivering conditioned air to the 4 zones. Ducts are routed to the left and right top sides of the fuselage to supply the compartments. The air then enters the cabin and circulates around. Part of the air flows rearward from the hat racks to be mixed with the air just leaving the duct. When the air cools down, it flows through the sidewalls down to the extraction duct system. The rack valve will improve the cooling of the electronic racks on the ground. The cooling medium is the air tapped off from the supply duct to the flight deck. The rack valve is controlled by a selector and the landing gear air-ground logic. The valve position is shown with a magnetic indicator. An amber fault light illuminates only on the ground to indicate a failure of the electronic rack's ventilation. The light is accompanied by an external horn to attract the ground mechanic's attention. 2 electrical fans are used to ventilate the avionics flight deck instrument panel, forward and center galleys, forward toilets, and batteries. The fans are associated with a ducting system to extract the used air from these areas and feed it to a plenum chamber. The air is then dumped overboard. The fans are controlled by a selector and their condition will be shown by magnetic indicators. The fans run automatically as soon as electrical power is supplied. When the differential pressure increases above 1 psi, the fans stop running and ventilation is provided by differential pressure. What caused the fault light to illuminate? Cargo heating is provided for the aft cargo compartment. The air used for heating is the air discharged from the cabin and hot trim air from the hot manifold. Air from the hot manifold will supply the aft cargo compartment through a hot air valve. The valve position is shown by a magnetic indicator. Temperature regulation is such that hot air is added to the cabin air through temperature control valve. The regulation of the temperature control valve is done with a rotary selector and the valve position is displayed on a position indicator. Isolation valves are provided to shut off the airflow in case of an internal cargo fire. Valve position is shown by a magnetic indicator. These indicators reflect the ambient temperature from the forward and aft compartments. A fan is installed in the extraction system of the aft cargo compartment. It extracts the air from the aft toilet and aft galley into a plenum chamber where the air is then dumped overboard. Control of this fan is with the toilet, galley, and cargo fan switch. Operation is like the main and battery fan. The main battery and toilet galley aft cargo fans are controlled through Let's look at the last subsystem, the pressurization. Its purpose is to establish and maintain a selected cabin altitude to control the rate of cabin variation and to limit the cabin differential pressure. Monitoring and controls are located on the cabin pressure panel. Pressure regulation is carried out by 2 independent but identical semi-automatic systems. While one system is operative, the other one is on standby. There are 2 forward and 2 aft outflow valves. Each regulating system controls, via a controller, 1 forward and 1 aft outflow valve. System selection is controlled by a system select switch, and the position of the 4 outflow valves is reflected by dual needles on the 2 valve position indicators. Management of the pressurization system is accomplished with a cabin pressure regulator and with other input signals. The controller transmits an electric signal which actuates a motor on the outflow valves. The 3 rotary knobs mounted on each pressure regulator are for setting the cabin altitude, the cabin rate of change, and the barometric correction. While the aircraft is on the ground, surges or overpressure is prevented by a ground auxiliary valve. This valve is automatically controlled through the ground auxiliary valve switch and by input signals from the throttle position and landing gear air-ground logic. The fault light is a disagreement light. 3 instruments display cabin differential pressure, cabin vertical speed, and cabin altitude. A red pressure highlight illuminates when the cabin pressure differential is more than 8.85 psi. Also, red altitude light will illuminate if the cabin altitude climbs above 10,000 feet. If the 2 semi-automatic systems fail, there is still a manually operated emergency system to discharge the air. The valve is controlled by a hand wheel on the left-hand side of the flight engineer's panel. What does this light mean? Let's review the air conditioning system. The hot air from the pneumatic system passes through a pack valve and a flow limiting valve to enter the pack. Cool air leaves the pack to supply the cold manifold. Part of the hot air enters the hot manifold via a trim air valve. Temperature adjustment for the compartments is accomplished with the temperature control valves. Temperature sensors monitor the duct and zone temperature. The used air is then dumped overboard by the fans. Air used for heating the aft cargo compartment is cabin air and hot air from the hot manifold. Pressurization control is accomplished with 2 semi-automatic systems and an emergency depressurization system. This concludes the presentation of the A300 air conditioning systems.
This program describes the A300 hydraulic power generation system. Hydraulic power is required for operation of the flight controls, landing gear, and cargo doors. The hydraulic system is composed of 3 independent subsystems which are designated by the colors blue, green, and yellow. The flight controls are supplied from all 3 subsystems. The landing gear systems receive green and yellow power. The cargo doors operate only on yellow. Each of the 3 power generation systems is of conventional design. This drawing is typical. It shows a reservoir or tank from which a pump draws fluid by suction. The pump delivers high pressure through manifolds to the users, that is, the components to be powered. An accumulator is shown connected to the high pressure manifold. The lubricating fluid from the pump returns to the reservoir through a case drain line. The normal operating pressure in each of the 3 systems is 3,000 psi, and the operating temperature is about 30 degrees centigrade. The 3 hydraulic systems are controlled and monitored on the hydraulic control module located on the upper left side of the second officer's panel. The hydraulic control module is divided vertically into 3 sections to represent visually the 3 systems, which are, from left to right, blue, green, and yellow. Moreover, proceeding from the bottom of the module to the top, the physical arrangement of the controls and indicators displays logically the flow of hydraulic fluid from the tanks to the pumps and then to the pressurized systems. Each reservoir is monitored by a quantity gauge and 3 amber lights which indicate air pressure low, temperature high, and level low. The green arc on the quantity gauge represents the normal operating range. The nominal level is marked by a short red arc outside of the green arc. The yellow arc shows the low-level condition. Included in the yellow arc is a red dot, which corresponds with the low-level warning. When the indicator needle drops to this red point, the level low warning is triggered and the amber light illuminates. The capital letter T, which appears in the lower left corner of the warning light, stands for test. The T signifies that the warning circuit may be tested by pressing the light caption. The capital D in the lower right corner means that the light may be dimmed. Illumination of the temperature highlight indicates excessive temperature of the fluid being returned to the tank. Note that the warning circuit may be tested by pressing the light, but the light cannot be dimmed. The air pressure low warning light monitors the head pressure of the reservoir. In order to ensure positive fluid pressure to the pumps, each of the tanks is pressurized to approximately 50 psi by the pneumatic system. Although the APU bleed air can supply the tanks through the pneumatic system, the pressure is insufficient to provide 50 psi. Bleed air from the engines or a high-pressure ground unit is required for full pressurization. Once pressurized, a reservoir should hold pressure for 3 hours without a bleed air supply. Whenever the air pressure drops to a predetermined value, the air pressure low warning light will illuminate. The main power sources are 4 engine-driven, self-regulating pumps, each of which produces 3,000 psi. This illustration shows that number 1 engine drives a green and a blue pump, while number 2 engine drives a green and a yellow pump. Thus, the pumps are installed in such a manner as to keep 2 hydraulic systems functioning should one engine fail. Schematically, this design principle is shown here. Note that with an engine failure, the green system remains operational along with the blue or the yellow system. On the left of the control module are located the two engine pump selectors for number 1 engine. One selector for the blue pump and one for the green pump. The guards on these selectors are color-coded appropriately for the two hydraulic systems. On the right side of the control module are the selectors for the pumps mounted on number 2 engine, one green and one yellow. Again, notice the appropriate color coding on the guards. The normal position for a pump selector is on. The associated engine pump magnetic indicator, or MI, which monitors the pump's outlet pressure, will be amber until the engine is rotating, at which time the MI will go in line, signifying that the related pump is now producing pressure. Here, the number 2 engine has been started. Consequently, the green and yellow systems are being pressurized. Three pressure gauges located at the top of the control module register the pressure being produced in each system. In addition, 3 amber low-pressure warning lights monitor pressure. A low-pressure warning light will illuminate if a system's pressure drops to less than 1,450 psi. Placing an engine pump selector to the dump position causes the related pump to be depressurized and self-lubricated. This is the most common action in responding to an hydraulic power problem. Observe here that as a result of placing the yellow pump to dump, the pump's MI has turned amber, and the yellow system pressure gauge indication has dropped to less than 1,450 psi. Accordingly, the low pressure warning light next to the pressure gauge has illuminated. If a pump selector is moved to the shut valve's position, the supply of fluid to the related pump will be stopped by closure of the respective tank shutoff valve. The closure of the valve will be enunciated by this magnetic indicator going cross-line. The shut valve's condition also stops the return of lubricating fluid from the pump. If a pump remains in this isolated condition for approximately 3 minutes, it will be damaged. If a fire handle is pulled, it causes the tank shutoff valve in each of the affected hydraulic systems to go closed. A tank shutoff valve is also referred to as a fire shutoff valve. With the fire handle pulled, the two related tank shutoff valve MIs will go cross-line, confirming closure of the valves. Each of the hydraulic systems is provided with backup pumps. The green system has 2 AC electric motor-driven pumps. The 2 control switches are located as shown here. These electric pumps make it possible for the green system to be pressurized for hydraulic ground test, for an auxiliary power source, and for emergency reasons. One magnetic indicator monitors the outlet pressure of the pumps. The MI will be cross-line until one or both pumps are turned on. Then the MI should go in line. The flow rate of the electric pumps is reduced from that of the engine-driven pumps, and they are used primarily for ground test operations. These two on-off switches control the operation of two installations called power transfer units, or PTUs, which are backup pressure sources for the blue and yellow systems. The PTUs permit the blue or the yellow system to be pressurized from the green system. They consist of pumps in the blue and yellow systems driven by hydraulic motors in the green system. In this type of motor pump arrangement, there is a transfer of mechanical energy without a transfer of fluid. The PTUs are used for hydraulic ground test and for an auxiliary power source. They deliver 2,500 psi. An example of hydraulic ground test is shown here. The engines are not running. The green system is being pressurized by its two electric pumps. The right-hand PTU switch is on. Thus, green system pressure is driving the motor pump and pressurizing the yellow system. Note the pressure of about 2,500 psi registered on the yellow system pressure gauge. Because of the low flow rate of the AC electric pumps, only one PTU should be used at a time when the green system is pressurized by the electric pumps. Here is an example of a PTU being used for auxiliary power. Assume an in-flight situation wherein the blue system pump has been put to dump as a result of a malfunction. Subsequently, the left PTU was turned on to power the blue system components. Again, note the pressure of 2,500 psi on the blue system pressure gauge. A backup electric pump partially supplies the yellow system. It is used to charge two accumulators for emergency braking and the parking brake. It is also used in conjunction with a hand pump to operate cargo doors. On the flight deck, the pump is controlled and monitored on this module, which is located on the pilot's overhead panel. Also, two control switches for the pump are located at the cargo doors. Accumulator pressure is produced by activation of this push button. The pressure is read on the gauge above the push button. This electric pump is self-regulated with a pressure output of 3,000 psi. This illustration shows the logical relationship of pump controls and the related section of the yellow system. The yellow system has another backup pump which is operated by a ram air turbine, or RAT. The RAT is installed in the lower inboard section of the right wing between number 2 engine and the fuselage. When the RAT is extended into the airstream, the hydraulic pump is driven by a variable pitch propeller which is completely effective down to an airspeed of 130 knots. The pump produces a pressure of 2,830 psi. The ram air turbine is extended by a spring-loaded device. Either of two control handles, one each on the captain's and first officer's side consoles, provides the means for extending the rat. Once it is extended, retraction can only be accomplished on the ground. In summary, there is a total of 7 backup pumps, 3 electric motor-driven pumps, 2 in the green system and 1 in the yellow system, 2 hydraulic motor-driven pumps, 1 in each PTU, 1 ram air turbine-driven pump. In addition, 1 hand pump is installed in the yellow system for cargo door operation. The 4 engine-driven pumps and 7 backup pumps are shown here, positioned in the hydraulic system layout. For operational understanding, the relationship of pump controls to pump positions in the system layout may be visualized by comparison of the control module and the schematic plan of the hydraulic power generation system. The warning circuits with amber warning lights on the hydraulic control module are integrated with a visual and an oral warning of the master warning system. The illustration locates amber lights of the warning circuits which are interfaced with the master warning system. When a warning circuit is triggered, both the related amber light on the control module and the amber hydraulic light on the master warning panel will illuminate. Simultaneously, a single stroke chime will sound. For example, the blue system indicators are shown here, reflecting a low-level condition. The quantity gauge needle is pointing to the red dot in the yellow arc. Triggering of the warning circuit causes the level low light to illuminate, the hydraulic light on the master warning panel to illuminate, and the single stroke chime to sound. It should be noted here that each of the amber light captions which contain a capital T can be pressed to test the entire warning circuit, including the warnings of the master warning system. An example is the level low light. A pump pressure low light, which is an amber arrow, monitors the outlet pressure of the 4 engine-driven pumps and the 2 green system electric pumps. If the electric pumps are being used and the pressure drops to a preset value, the light will come on. In this case, there will be no master warning system's signals. However, if the light illuminates in response to low outlet pressure of an engine-driven pump, the master warning system signals will be activated. The drawing on the left screen indicates that the yellow system's engine-driven pump is not producing sufficient pressure. In addition to the pump's MI being amber, the amber arrow is on. Accordingly, the master warning signals are activated. It has already been stated that combinations of the three hydraulic subsystems power the flight controls, landing gear systems, and cargo doors. The flight controls are divided into two categories: primary flight controls and secondary flight controls. This division is worthy of note since the hydraulic power combinations are different for the two categories. The primary flight controls consist of the following: left hand and right hand, all-speed aileron and low-speed aileron. 3 roll spoilers on each wing. Left hand and right hand elevators. Rudder and movable horizontal stabilizer. Normally, the primary flight controls are powered simultaneously by all 3 hydraulic systems operating in parallel. The secondary flight controls are as follows: 3 trailing edge flaps per wing, 3 leading edge slats per wing, 1 Kruger and notch flap per wing, 2 inner and 2 outer speed brakes per wing. The secondary flight controls are powered by 1 system or combinations of 2 of the 3 systems. Because of the various combinations of hydraulic power to the different users, certain details of hydraulic power distribution are operationally important. But complete mastery of the power sources for all using components should not be attempted at this time. Subsequent programs will expand this subject. On the blue power generation schematic, locate the 2 manifolds designated as servo control manifold and pressure manifold. The engine-driven pump pressurizes the servo control manifold, from which the pressure manifold is pressurized. The output of the power transfer unit goes directly to the pressure manifold. If the engine-driven pump is inoperative, the PTU can pressurize the servo control manifold through the pressure manifold. These 2 manifolds are the departure points for hydraulic power distribution to the using components. This extension of the schematic shows the components supplied by each manifold. The leading edge slats are supplied from the pressure manifold directly. However, a priority valve isolates the slats and gives priority to the servo control manifold in the event of a blue system pressure drop. The valve closes when system pressure falls below 1,885 psi. On the pilot's overhead panel is located a servo controls module. The blue servo control lever is pointed out here. The lever operates the servo control shutoff valve through which are supplied the units powered from the blue servo control manifold. The subject shutoff valve is represented on the blue system schematic being shown. It is labeled Servo Control Selector. Note the components powered from the servo control manifold. The green system servo control manifold is pressurized by the two engine-driven pumps. As with the blue system, the pressure manifold is normally pressurized through the servo control manifold. The output of the two electric pumps goes directly to the pressure manifold. On this schematic, locate the pressure manifold and note the components powered from that manifold. A priority valve is installed on the pressure manifold. The valve functions as described for the blue system. If green pressure drops below 1,885 psi, the valve will close, removing green system supply from the nose wheel steering system, landing gear, leading edge slats, Kruger flaps, and trailing edge flaps. The normal wheel brakes and the motors that drive the power transfer units are connected directly to the pressure manifold. The center servo control lever is for the green system. When the lever is moved to the off position, as shown here, green hydraulic power is removed from all those components which are normally supplied by the green servo control manifold. The blue and yellow levers have the same function for their respective systems. In general, the yellow power generation is the same as that for the blue and green systems. Some differences should be pointed out. Note that the yellow tank has a small sump at the bottom from which fluid is supplied to the ram air turbine. Also, the pressure manifold is divided into three parts. The left side is the same as the pressure manifold in the other two systems. The center part is equipped with two additional accumulators and can be pressurized through check valves from either the left or right side. The right side receives pressure from the electric pump or the hand pump. Moreover, the yellow system has two priority valves, one to isolate units powered by the pressure manifold, and another for the yellow supply to the horizontal stabilizer. The latter is shown at the top left side of the schematic. If system pressure drops below 1,885 psi, the valve closes, isolating the stabilizer from the servo control manifold. The yellow servo control lever and the related servo control manifold function as described for the other systems. The using components which are powered from the 3 servo control manifolds are shown here. Design redundancy, that is, provision for backup power in the event of failures, is obvious in the right-hand illustration. Each hydraulic system is provided with its own servicing panel, which is used to pressurize the system from ground carts. The common refilling connection for all reservoirs is located on the green servicing panel.
This presentation will cover the landing gear system of the A300 aircraft. The landing gear course is divided into the following parts: the introduction, in which we will begin with a general overview, and then the description, which begins with the extension and retraction system, followed by the brake system and nose wheel steering. The A300 is equipped with a conventional tricycle-type gear. In addition, there is a tail skid. Each main gear is provided with an oleo shock strut and a 4-wheel bogie beam. The nose gear is a twin-wheel steerable oleo shock strut assembly. The nose gear retracts forward, while the main gear retracts laterally inward. The hydraulically operated gear doors close after extension or retraction, while the doors that fare in the retract path operate with the gear struts. There is only one retraction system, but there are 3 extension possibilities: the normal extension system, an alternate extension system, and an emergency extension system. All 8 main wheels are supplied with brakes, none on the nose gear. There are, in addition to the parking brake system, 3 independent brake systems: the normal system, the alternate system, and the emergency brake system. The normal brake system and the alternate brake system are equipped with an anti-skid control system. Nose wheel steering is operated by 2 actuators supplied by the green and yellow hydraulic systems simultaneously. A tail skid absorbs the load which could damage the structure if the aft part of the aircraft comes into contact with the runway. Before we go any further, let's try a question. How many retraction and extension systems and how many brake systems does the aircraft have? B is the correct answer. Now let's look at the controls and indicators for the landing gear on the flight deck. The landing gear lever with the gear position indicator is on the center instrument panel. A second completely independent gear position indicator is located on the second officer's panel. For alternate and emergency extension, a hand crank is located in the right side console and can be inserted in a drum on the floor by the first officer's seat. Now, let's study the extension and retraction system along with the indications and warnings. There is a normal extension and retraction system supplied by the green hydraulic power system. An alternate extension system is mechanically controlled by the hand crank, which bypasses the green hydraulic system and supplies the landing gear with the yellow hydraulic system pressure. This same hand crank, rotated to its limit, mechanically unlocks the gear by cables for free fall. Let's look at the extension and retraction systems now. 3 systems allow the gear to be controlled. The normal system is powered by the green hydraulic system and is electrically controlled by a gear handle located on the center instrument panel. An alternate extension is powered by the yellow hydraulic system and is controlled mechanically by the hand cranked. All up locks are released hydraulically and extension is by free fall. All doors will remain open. The emergency system is controlled by the same hand crank. The up locks are released mechanically by cables and the extension is by free fall. Once again, all doors will remain open. Now, in more detail, the normal system is powered by the green hydraulic system for extension and retraction. The gear handle is provided with 3 positions, up, neutral, and down. The up and down signals are electrically transmitted to a gear selector valve controlling extension and retraction. When the handle is moved from one position to the other, a sequence is started. Doors open, gear unlocks and moves, and door closes. When the gear handle is in the down position, the gear will be locked down with the doors closed and the green lights will be illuminated. When the gear is in the up position and the landing gear will be locked up with the doors closed and the lights will be extinguished. Before the gear handle can be moved from down to up through neutral, 3 conditions must be satisfied. The nose gear must be fully extended and centered. Both main gear oleo struts must be fully extended, and both main gear trucks must be perpendicular to their struts. For safety reasons, 2 detection circuits have been supplied. They are selectable with a switch on the first officer's side console. Now, let's see how we are progressing by answering this question. What is the normal gear operation? A, B, or C? Normal gear operation is controlled electrically and sequenced hydraulically, so the correct choice is B. Let's look at a few more details about the alternate extension system. For alternate extension, the hand crank has to be turned approximately 14 turns. It operates an alternate selector to bypass the green system pressure and connect the yellow system pressure to the alternate up-lock release components. Extension is then done by free fall and the doors remain open. The emergency extension system gives us the 3rd possible way to extend the gear. It is operated by the same hand crank that was used for the alternate extension system. Remember, we used this hand crank to extend the gear when there was no green system pressure. 14 turns of the hand crank allowed us to connect yellow system pressure for free fall extension. In the absence of yellow pressure, an additional 4 turns, or the limit of cranking, will cause mechanical unlocking and the free fall of the gear. Now that we have seen the various ways of extending and retracting the landing gear, let's look at the gear indication and warning systems. 2 independent gear position indicators are provided, consisting of 3 amber door lights, 3 red unlock or transit lights, and 3 green arrows, signifying gear down lock on each indicator. There is 1 indicator above the gear lever and 1 indicator on the second officer's panel. The gear position indicators are electrically independent of each other. The door amber lights indicate the doors are not up-locked. The signal comes from the up-lock box. The red lights are gear disagreement, or, if you prefer, unlock lights. They come on when the gear position is not as selected. When the gear and doors are uplocked, all lights will be extinguished. If the electrical indication systems are not available, or if you desire a visual confirmation of a downlock condition on the main landing gear, mechanical pop-up indicators on the wing upper surface can be viewed from a cabin window. Pop-ups extended, geared down, and locked. The nose gear mechanical downlock indicator consists of a green flag. It is controlled by the drag strut and is visible from the electronic bay through a viewer. A second viewer permits the flag to be illuminated by a flashlight. For your information, the wheel well lights will automatically illuminate with the gear extended and electrical power on the aircraft. A continuous horn and red arrow are activated together in the gear warning configuration. In certain cases, the gear horn can be silenced by the audio cancel on the master warning panel or a gear horn off push button on the right side of the pedestal. The red arrow cannot be canceled except by removing the cause. As we know from previous aircraft models, a gear warning horn will sound whenever the gear is unsafe to land with certain conditions existing. On the A300, a continuous horn will sound and be accompanied by an illuminated down red arrow under 3 different conditions. First, with both engines running at an N1 speed less than 75%, or only one engine running at an N1 speed less than 97%, slats and flaps 0 and the aircraft speed less than 200 knots. The horn can be canceled by the audio cancel switch on the master warning panel or the gear horn off push button on the pedestal. Second, with the N1 speed as mentioned previously, flaps and slats in a position other than fully retracted or extended, and the aircraft speed less than 100 knots. This horn can also be canceled as mentioned previously. Both conditions that will cause the continuous horn to sound and the red arrow to illuminate depend on a radio altitude of 1,000 feet or less. The third situation is, regardless of the engine RPM or airspeed, the red down arrow will illuminate and a continuous horn will sound if the flaps and slats are fully extended, 25 degrees, and the gear is unsafe to land regardless of the radio altitude. The horn cannot be canceled except by removing the cause. With all the components for extension and retraction, controls and indicators shown here, take time and review their location. We will resume again with the brake systems. The brake system is divided into 4 subsystems: the normal brake system, alternate brake system, emergency brake system, and the parking brake system. As we mentioned earlier, only the main gear wheels are equipped with brakes. Each brake consists of 2 sets of pistons, green system pistons and yellow system pistons. The normal brake system is an electro-hydraulically controlled system. An electric transmitter, driven by the brake pedals, signals the amount of brake pressure to be applied, which is then modulated by anti-skid valves on each wheel brake. As soon as one pedal is depressed, a switch in the electrical transmitter will open the green supply valve to distribute the green hydraulic pressure to the anti-skid valves, which are modulated by the brake pedal position transmitters. 2 master cylinders connected to the brake pedals provide artificial feel. Eight independent electric control channels are provided to transmit pedal position signals to each individual anti-skid valve. Each anti-skid valve also receives a signal from the anti-skid system box, which means that each individual anti-skid valve receives 2 independent electrical signals. The anti-skid valve modulates the brake pressure proportional to brake pedal position. If a wheel tends to skid, the anti-skid control box will send a counteracting signal to the valve on the skidding wheel to release the brake. The anti-skid box output signal is distributed to the normal anti-skid valves, shown in blue, and to the alternate anti-skid valves, shown in red. We will discuss the alternate brake system later. The anti-skid release signal is generated by comparing the speed of the nose wheel with the speed of the main wheel. These speed signals come from speed sensors on each aircraft wheel. The nose wheel speed sensors are dual for safety reasons. During brake application, if the speed of the main and nose wheels stay within an acceptable range, the anti-skid box will not send a release signal. But if the main wheel begins to skid, the difference in speed between the main wheel and the nose wheel will increase, and the anti-skid box will send a release signal to the corresponding wheel. Located on the overhead switch panel is an anti-skid monitoring unit. It consists of 8 R lights, a brake and anti-skid control switch, and 2 ground test switches. If the anti-skid system is turned off or has failed, an amber anti-skid off light on the master warning panel will illuminate and a single-stroke chime will sound. Ground tests for each individual nose wheel speed sensor can be accomplished by depressing the test switch one at a time. The anti-skid system provides optimum braking effect and protection against locked or skidding main wheels. When the aircraft ground speed is below a certain value, braking is regulated but not optimized. Above a certain value, braking is regulated and optimized. In either case, locked wheel protection is available. When a main wheel skids, the anti-skid valve will release the pressure to the brake and illuminate the applicable R light. This action is accomplished by comparing the speed of the nose wheel with that of the main wheels. After takeoff, with the gear lever in neutral, the anti-skid system is de-energized. On approach, with the gear lever in the down position and the gear extended, touchdown protection is provided to prevent landing with locked wheels. A theoretical 100-knot speed signal is sent from the nose wheel sensors so that all release lights will be illuminated and the brakes will be released. If the nose gear is held off the ground, braking action will start when the main wheel senses 100 knots. Anti-skid protection is available at this time. After the nose gear is on the ground during rollout, braking action is regulated and optimized when the aircraft is slowed down to less than 40 knots. Braking action is regulated but not optimized. After the aircraft has stopped, maximum braking is possible, and no release signal can be emitted. Test your memory with this question. The anti-skid system The correct answer is B. Now, let's look at the alternate braking system. Yellow system hydraulic pressure supplies 8 alternate anti-skid valves and uses circuitry and accessories independent of the normal brake system. Transfer from the normal to alternate system is automatic if green hydraulic pressure is lost, or if the anti-skid switch is moved to the alternate position. Yellow system pressure is modulated by dual progressive distributor controlled hydraulically by a low pressure or master cylinder type circuit. This modulated pressure is delivered to the 4 alternate anti-skid valves of each gear and is monitored by a dual brake pressure indicator. The alternate braking effect is the same as that of the normal braking system, since the alternate anti-skid valves receive a release signal at the same time as the normal anti-skid valves. Yellow alternate system brake pressure is read on this dual indicator located on the center instrument panel. Now for the emergency braking system. The emergency system uses the same hydraulic circuitry as the alternate brake system and is automatically selected if the yellow system pressure fails. The hydraulic power comes from the brake accumulators. Braking pressure is modulated by the brake pedals, and pressure is monitored by the dual brake pressure indicator. In this case, there is no anti-skid protection available, and 7 full brake applications are available. The 2 yellow brake accumulators can be monitored and recharged from the overhead switch panel. And now the parking brake system. Yellow system accumulator pressure is also used to apply the parking brake. The system is controlled by the parking brake handle. Without regard to brake pedal position, when the parking brake handle is pulled, accumulator pressure is directed simultaneously to the 8 brakes. The dual progressive distributor is bypassed, and parking brake pressure is indicated on the dual brake pressure indicator. As soon as the parking brake handle is pulled, a parking brake amber light on the master warning panel will be illuminated. Try this question. The alternate braking system is monitored by answer A, B, or C. The correct answer is C. The dual pressure indicator and the anti-skid system monitors the alternate braking system. After takeoff, the nose wheel rotation is automatically stopped when the tires come in contact with brake shoes in the wheel well. The main wheels are automatically stopped by the in-flight braking system when the gear lever is moved to the up position. A brake temperature monitoring unit located on the second officer's panel is equipped with an indicator, 8 amber warning lights, and a test switch. The brake temperature indicator displays the temperature of the hottest brake. When a brake hot light is pressed, it will read the temperature of that brake. An amber brake hot light will illuminate when the temperature of the brake reaches 185 degrees centigrade. The test switch tests all brake hot lights, and the brake temperature indicator shows 250 degrees centigrade above the hottest brake. To prevent takeoff with a hot brake, if the N1 RPM is greater than 97%, an amber brake's hot light will illuminate and a single-stroke chime will sound. To help keep the brakes cool, a brake cooling fan is installed on each main landing gear wheel. All 8 fans are controlled by a brake fan switch located on the second officer's panel. Now, a question concerning the brakes. How are the parking brakes operated? Remember, on the A300, it is only necessary to pull the parking brake handle to set the brakes. A is the correct answer. Now for the last subsection, the nose wheel steering system. 3 steering ranges are possible: 6 degrees by the rudder pedals, 65 degrees by steering wheels, and 100 degrees with a towing bar. 2 steering handles are provided, located on each side console. The nose wheel steering system is a duplex hydraulic system supplied by the green and yellow hydraulic systems simultaneously. The dual steering control valve is operated by mechanical inputs. The control mechanism consists of a rudder and steering handle linkage. In order to have nose wheel steering on the ground, 2 electrically operated hydraulic supply valves must be opened. The valves open automatically when the nose gear and left main landing gear struts are compressed and the towing lever is in the normal position. With green and yellow hydraulic pressure available, The rudder engagement unit and the dual steering control valves are supplied simultaneously. The green and yellow hydraulic lines are independent of each other, and one system by itself can provide nose wheel steering. Between the actuators on the left-hand side of the nose gear is a nose wheel steering deactivation system, also called the towing handle. When this handle is turned off, the two hydraulic supply valves close, deactivating the nose steering system. For deactivation, turn the handle and insert the safety pin. A few words about the tail skid, which is installed to protect the tail cone from an excessive body angle on the ground. It is merely a shoe which is not retractable, covered by a fairing. On landing with the struts compressed, a body angle of approximately 13.5 degrees will help polish your shoe. Let's try two questions before we finish. Maximum nose wheel steering deflection given by handle is? The answer is C. The nose wheel steering system is provided hydraulically. The answer is A. Now, let's cover the A300 auto braking system. It is a system that permits auto brake application without brake pedal deflection. The advantages gained by using this system are: it relieves the pilot of the braking task to get optimum deceleration according to aircraft weight and runway length, and improves tire and brake wear. It also reduces the stopping distance in the event of an aborted takeoff and improves passenger comfort due to a consistent deceleration rate. As a reminder first of the operation without an auto brake system, the brake signal is initiated by the pilot and transmitted to the anti-skid valve. The anti-skid control box will modify the brake signal to prevent locked or skidding wheels. With an auto brake system, the braking order is initiated by the auto brake control box. It is operational only when using the normal brake system. The auto brake selection panel is located on the center instrument panel below the engine instruments. This panel will allow the selection of 4 braking modes, which can be overridden by the pilot depressing his brake pedals. The panel consists of 4 mode engagement push buttons marked minimum, medium, high, and maximum, and 1 push button labeled auto brake, which has 2 functions. First, it functions as an on-off switch. Second, it is used as a warning light. That is, it will flash for approximately 10 seconds when the auto brake system has been disarmed. Now let's see how the system operates. The auto brake system is armed only if the conditions seen on the screen are fulfilled. If any one of these conditions is not met, after a mode has been engaged, the auto brake amber light will flash for 10 seconds. As already stated, the mode can be disengaged by depressing the brake pedals. When a mode is engaged, the upper portion of the push button illuminates white. When cleared for takeoff, the system is to be selected to the maximum mode and the white portion of the push button should illuminate. In case of an aborted takeoff, maximum braking is automatically applied when the ground spoilers are extended. Immediately, the green light will come on when braking action starts. During approach, a mode will be engaged considering landing weight and runway length. As soon as the mode is selected, the white portion of the push button is illuminated. After touchdown, as soon as the ground spoilers extend, braking is automatically applied as long as the aircraft is rolling. When the aircraft deceleration rate reaches the one selected, The white light extinguishes and the lower part of the push button illuminates green. Braking action is automatically canceled when the spoilers are retracted. The white light will come on again, indicating that the mode is still engaged. At any time, one mode can be replaced by another one. Depressing the auto brake push button or the landing gear retracting causes the mode disarming without the auto brake light flashing. The auto brake system is not connected to the master warning system. This concludes the auto brake system presentation.